Okay, so now we're going to get into some cool stuff. So today's lecture, lecture 8, is about forces, vectors, equilibrium, and reactions. Basically, we're going to start talking about this concept of statics. Now, if you guys remember for your project, I've said you have to pick a static object. And what that means is an object that's not moving. If it's moving, you're not in the course we're talking about. We don't want our buildings to move. Deflection is different than movement, remember. We don't want our buildings to move, so we need them to be static. You tend to be able to look at something and see if it's static. Now, static, remember, it's not moving, which means it is stable. If something's not stable, it's going to slip or slide or tip. It's going to move in some way that we don't want it to. So what we're going to actually start doing is quantifying this idea of stable. Remember, we have strong enough, stiff enough, and stable. So we've talked a little bit about the things that go on an object so that we can start talking about strength. Now we need to talk about stable. And the things we're going to talk about today are going to be us beginning this process of proving something stable. Now we kind of go over it in over two separate weeks, and it's this introduction of statics. So if I am standing here like this, you know I'm not sinking down to the center of the world. Something is stopping me from sinking down into the center of the world. You know that it's the ground, or not even the ground, the floor. I'm standing on the floor, and it's stopping me from going down into the center of the world. So then what's happening with my load on the floor? Well, we don't know exactly what you don't know exactly what the construction is under there, but I'm going to tell you I was standing over a joist. So I'm standing over a joist, the load's going to move to the two ends, and then there's going to be something that stops that joist from going down into the ground. Well, probably there's a wall underneath it. Well, then the load's going to go down the wall. What stops the wall from going down into the center of the earth? Well, there's probably a footing or a basement down there that's sitting on the ground. And then the ground is the thing that stops us from going down into the center of the earth. We're going to start beginning the process of documenting that, essentially. But drawing me standing on a joist, that seems a bit complicated. What if, like me, you're not a very good artist? Now, you guys, all being in architecture, are probably pretty good at drawing things. But us engineers, not so much. We're really bad at it. So we usually try to do simple things to represent what's happening. And that's where arrows become our friends. We will often draw the loads that are applied on things using arrows. Now, you've probably seen it already. Intuitively, you probably get your head around that, and the arrow shows what direction that load is going. Well, those are our forces. We're going to represent our forces as an arrow. Now, when you have a force with an arrow, it's telling you a value and a direction. Something that has a value and a direction has a very specific term. And I don't want you to get too caught up on it, but it's called a vector. And vectors are kind of neat because there are some cool things we can do with vectors. Now, you've probably all done at least one physics class, and you're going to think way back to it, because really what I'm going to be talking about today is stuff you did in grade 10 physics. There's not much new. I'm applying it to something very specific, but I remember my grade 10 physics textbook, and I can tell you that a lot of these problems are simpler than that. So we're going to go back, we're going to relate it to basic trigonometry, and we're going to talk about what we can do with vectors. Now, most of the time for us, vectors are going to be forces. But they don't have to be. They can represent other things. They can represent direction. They can represent velocity. They can represent acceleration. They can even represent moment, which I'm going to talk about next week, because moment is another thing we use a lot. So just try to remember that everything we're doing today is about formalizing what we intuitively already know. Okay? Just whenever you start to get overwhelmed by it, stop, take a break, and think, what is the goal of what we're talking about here? What is this thing that's happening? And take a breath, think about that, and then jump back into the math. And I usually always try to do a little exercise in the top corner of the page that helps me out with that. Basically, I make a pretty darn good guess about what the answer is going to be, so that when I go through the math, I can see that it matches what my guess was. Okay. So statics. Now, I've already talked about a bunch of this, so here I'm going to give you all kinds of really boring definitions. Statics, the branch of mechanics that is concerned with the analysis of loads, so force and torque and moment, on physical systems in static equilibrium. That is, in a state where the relative position of subsystems do not vary over time, or where components and structures are at a constant velocity. Basically, if I have this object, it's not moving up and down, it's not moving back and forth, and it's not moving in and out of the page. So we've got 3 directions where this thing can move. Some of you are already saying, wait, I know there's more that could happen. But this week, we're just going to talk about those 3 things. Up and down, back and forth, and in and out of the page. Basically, they stay still. We're just going to formalize something staying still. So if this is an object pushing down and we represent it as an arrow pushing down, what would we do to draw the ground stopping it? Yeah, we'll draw another arrow going in the other direction. If you remember that, you've already got the rest of this lecture aced. But we're going to do math to prove some of this. All right, force. Force is Newton's second law. Don't worry about the definition too much of this. We're going to use it a little bit later in the term, but that's more to just show a fun little exercise. We're not going to get too caught up on force is mass times acceleration. But that is the principle of Newton's second law. Force is the product of mass and acceleration. I always remember that story of figuring out the difference between weight and mass, because they're not the same thing. We tend to, because we're on Earth, and acceleration doesn't tend to change when you're just kind of standing around or not moving, and we are not moving because we're talking about statics, that we tend to get weight and mass confused. But we're going to be talking about force. Now, force is mass in kilograms times acceleration, which, if you guys remember, is meters per second squared. Well, calling whatever our force is kilograms meters per second squared is a bit of a pain in the ass of a unit. It's such a kind of crazy unit that they actually decided to give it its own name. And that is, for those of you who like apples, a newton. Okay, so force has magnitude and direction is represented by a vector. 1 newton is 1 kilogram meter per second squared, and 1,000 of those is a kilonewton. So a newton is 1 kilogram times 1 meter per second squared. Okay, we often talk about it in kilonewtons or 1,000 of those things. All right, remember, we want to talk about this force as a vector. We don't know what a vector is, but here's a force. This thing is trying to move in this direction. We don't really know, is it kind of moving that way? Is it, it's hard to tell drawing this in 3D. So this is where things are going to start to get important about how we talk about things. All right, vectors are a way we can talk about force, or we can use this concept of vectors. Vectors are, we would just call force that had a line on top. It's representing a vector. It can let us know, hey, this isn't just a normal number, it's actually a vector number. If we have sidebars on it, we're saying that there's magnitude with no associated direction. We don't know where it's going. But vectors need a magnitude and a direction. So if we have a value with no lines or no sidebars, we need something to tell us its direction. So the value would be our magnitude. So the direction must be implied from context, like an arrow. An arrow gives you directional context. We can determine its direction from that arrow. This is what we're going to do the majority of the time. So the arrow is really important. Drawing that arrow with that value constitutes a vector. The reason it's important to know about vectors is because how we do math with vectors is different than regular math. So if we have a vector with a subscript x, y, or z, we're usually that means that we're talking about a force or a vector that's along a parallel axis. So if it is going up or down, it's along. If it says y, it's going up or down and it's on the y-axis. If it has a subscript x, it's going in this direction, which is our x-axis. If it has a subscript z, it's going in and out of the page, which is our z-axis. Oh, look, I'm cutting us off a little bit here. Let me move me. If you see a number 1 or a number 2 or a number 3 or a number n, it usually means that we have a bunch of vectors. Maybe it's A, B, C, D. I don't know. But usually that subscript that's not X, Y, or Z means that we've got a few of them. And so we need to do something with them. Or we don't, but they're letting us know that there's multiple vectors that we're looking at. So adding vectors. Vectors can be added graphically by connecting vectors from the tip to the tail. The sum of all the vectors is the vector from the first tail to the final tip. So it's often called tip to tail method, but it's tail to tip, really. So don't worry about that too much, but here's the process. Okay, I've got vector 1. It doesn't have the little line on top, but I know it's a vector because I've got an arrow. It's got a little subscript 1, so I can probably infer that there's more of these coming. There's more vectors coming. Okay, so this one is on the x-axis. This one's on the y-axis. Okay, this one's got a subscript 2. Oh, I've got F3. This one, some portion of it's going in the x direction and some portion of it's going in the y direction. And I've got F4. So I've got 4 vectors here. How do I add these up? Well, don't worry, I'm going to teach you the math in a few minutes, but graphically, there's a really easy way to do this. And if you have software that is to scale, like AutoCAD, you can actually do this and get exact numbers. So if I want to add all these up. I can draw one new vector that starts at the tail of the first vector and finishes at the tip of the last vector. So I want to know F1 plus F2 plus F3 plus F4. So look here, I've got the little hats on here because that's reminding me that these are vectors. And when I am drawing them right here, I don't have direction. So it's important to know that there's something going on. But I want to know what the total vector is, the total vector here. Look at this. If I start here and draw a line to here, I've got my answer. I still don't know what the value is, but if I drew this in AutoCAD and it was to scale, I could probably figure it out. It's got direction because it's got an arrow. We don't know what the exact number is, but we know it's some amount up off the x-axis. Okay, we can break vectors up as well. So if we have a vector, we could break it up into its parallel components. Remember I said if they have a subscript x, y, or z, that means it's on a principal axis? Well, that can be really handy for us, and we'll talk about that in a few minutes. But for those of you that remember right angle triangles, it's going to be super handy. All right, if we have this vector f, so it starts here and it comes to here, so we've got a magnitude and a direction, we can break this up into its x component and its y component. Remember, if we were adding those subcomponents up, it should start here and end here. So we've got fx and we've got fy. We know this must be true because it follows the tip to tail rule, or the tail to tip rule. This plus this has to equal this. Now what does this look like? This looks like a right angle triangle. what would the value of this line be? Well, for those of you that remember Pythagorean's theorem, you're probably already there. Let's take a look at the next slide. We want to know what fx plus fy is. What is that value? Okay, so if we had this, we recognize that this is a right angle triangle, and we know that the square of this plus the square of this equals the square of this. That is true for right angle triangles. So what we're really saying is fx squared plus fxy equals f squared. So f equals the square root of fx squared plus fy squared. So this was the same as our fx with the line over it plus fy with the line over it equals f with the line over it. Those little lines reminded us that it's not normal addition because they are vectors. All right, we've got a right angle triangle here. What are some other things we could do? Like if this is our f, we could probably actually quantify its direction. We know its value, and the arrows are really darn good at representing the direction. But what if we're not expert drawers? AutoCAD, yeah, we could draw it perfectly. But for me, drawing it on a piece of paper, it's going to be pretty good, and I could get out a ruler and measure things. But knowing what that exact value is would really allow me to quantify what its direction is. I would have some numerical value I could use to represent its direction. So sine, cosine, tangent is really helpful for a right angle triangle. This is our opposite side, this is our adjacent side, and this is our hypotenuse. So let's take a look. Sine of the angle equals fy divided by f. Cosine of the angle equals fx divided by f. And the tangent of the angle is fy divided by fx. Now you'll see that I drew this angle off of the x-axis. If we had been talking about this angle here, fx and fy relative to sine, cosine, and tangent would change because the opposite side is different. I'm a lazy person. I am always going to represent everything relative to the x-axis just to make my life easier, and then these three rules written just like this will always be true. Don't worry, I'm going to do one example today where I look at it from not the x-axis. You can do it however you like, but if you're lazy like me and you want to follow my methods, it's probably going to be easiest if you do all of your lines relative to the x-axis. Represent all of your vectors' directions relative to the x-axis. It's going to be super handy because we're lazy, and that means we can start to get really quick at doing this process. Because I can tell you, we're gonna do it a lot. When we do our trusses, you're gonna do these equations like 15 times. Okay, what if this was in 3D? Same rules still apply. I don't know if you know this, but Pythagorean's theorem applies in 3D as well as in 2D. So I can draw this vector. It's hard to graphically tell. Like you could say, this is just on the y-x plane, and that's it right there. We don't know, graphically looking at this in 2D, what its 3D component is. It's really hard to represent. And that's why having these numbers written in is very important. We're not really going to work in 3D. We're going to be lazy and always work in 2D, but it's good to know that these rules apply in 3D as well. So look at this. This vector actually comes out of the page some, and it wasn't easy to tell that by looking at this arrow. But it looks like there's an x component, a z component, and a y component. But the tip to tail rules still apply. So we have those three components. You know what I'm going to do? I'm even going to add in this graphic as a tail to tip method. So slide 9, add tail to tip. So I'm going to add that in for you guys, just because it's really nice to see that if you drew all of these as tail to tip, this still holds true. That addition, that graphical method of adding these up still works. But we can do it mathematically. fy squared plus fx squared plus fz squared equals f squared. The rules still apply. So you see, we put the little line over this to remind ourselves that as much as we're saying we're adding them up, it's not normal addition because it's vectors. But along the same axes, the life gets really easy. Okay, non-orthogonal components. It's easiest for us to break it up into x, y, and z because x, y, and z we can add linearly and then do something with. So what if we didn't have graphical software and we needed to add multiple vectors that didn't align to a normal axis or a principal axis? So we have f1 and f2, and we want to know what the total of f1 plus f2 is. It's not a right angle, so we can't use Pythagorean's theorem or sine, cosine, tangent to add these up. We need to do something else. We need another method to add these up. We do know that we can break f1 into its x and y component, and we can break f2 into its x and y component, and then everything on the x-axis we can add up linearly, and everything on the y-axis we could add up linearly. So then we have a total for the x-axis and we have a total for the y-axis. Well, then we're back into having a right angle triangle and we can do something with that. So let's take a look at that process. So let's break f1 into f1x and f1y. We can break f2 into f2x and f2y. And look, the same tip to tail rule applies. Like we know, or tail to tip, we can start here and draw that. Well, these still hold true. We can draw this and draw this and draw this and draw this, and we still get to the same spot. So we know graphically that this is true. We know that we can use a right angle triangle to determine these, and we can use a right angle triangle to determine these. Well, now we could add up f1x and f2x, f1y and f2y. So we've got a total here and a total here. And now we've just got a brand new gigantic right angle triangle that we can figure out what f is. So f1x plus f2x equals fx. f1y plus f2y equals fy. So really what we've done is a big long equation here, but always try to start with it graphically. It's going to really help you to look at it graphically. We're going to do a bunch of examples, so don't worry. We're going to draw it out. We're going to go through a bunch of these examples, so you don't need to panic too much. I'm going to show you the process to do this. Well, let's start with this one. Let's determine the total vector. We want to add these up. We want f1 plus f2 plus f3. They have given us the angles. So f3, they've given us the angle relative to the x-axis. F2, they've given us the angle relative to the y-axis. Now remember I said I'm lazy and I like to do everything relative to the x-axis? I'm going to show you that we can use the y-axis. I'm also going to take that and turn it into an angle reference to the x-axis, just to show that both ways work, but I'm lazy and I like to always do it relative to the x-axis. And then f1 is relative to the x-axis. So they've given us the values of all of these, or the magnitudes, and they've given us the direction by including the angles. Wait a second, didn't I say forces were in kilonewtons? I did, but it doesn't look like this is a force. They just said determine the resulting vector. They happened to call it F, but we don't know what they're using that for. These are in meters. So imagine someone walked this length, and walked this length. Would there be a shorter way to get to the final destination? So there are 3 lengths that somebody walks, and we want to see where they end up. Okay? Let's draw it. Let's do it tip to tail. I'm gonna change all these to tail to tip. because I find the name of it really annoying. That's the standard name for it. But really, we're starting at the tail and drawing it to the tip. All right, let's draw those 3 vectors. There's vector, these are our 3 vectors. So we start here and draw it to here. Perfect. Now, I know at least one of you is saying, how do I know what order to draw these in? And this is the best part. It doesn't matter. You can draw them in whatever order you want. This holds true. Now, there's always people who do not believe me for whatever reason, but I'm going to show you. All right, so this is one particular order that I picked at random to draw those 3 vectors, F1, F2, and F3 that happen to be in meters. So somebody walked this distance, and walked this distance, and ended up here. That is the equivalent of walking right to here. They could get to that point just by walking this length. Let's draw it in another order. These are the same 3 vectors. Haven't changed them. I literally copied the slide and moved them to a different order. But you start here and end here. That's the same resulting vector. That's the same answer. You can start here and get here. So it doesn't matter what order you follow these 3 vectors, the result is going to get you to here. Let's do it in another order. Okay, this one looks a little bit different. I'm going to start here, follow this vector, and follow this vector. Again, doesn't matter. Start here, end up here. It doesn't matter what order we do it in. The same resulting vector is going to get us to the exact same spot. Okay, let's do the same thing, but let's do it mathematically, okay? And none of these are on a principal axis, so adding them up, we cannot use Pythagorean's theorem, and we cannot use our sine, cosine, tangent rules. So what we need to do is break each one of these up into their x and y components, add up all the x components, add up all the y components, and then use Pythagorean's theorem to find the resulting vector. Okay, let's make me gigantic and turn our paper down here. Why am I crooked here? Ugh, I don't have it in the... There we are. Okay. One, two, three. All right. So we were given 3 separate vectors. We're going to start by breaking them down into their x and y components. We've already done a guess. Remember, we drew what we thought that should be in the end. And there was a vector that kind of went at a certain angle. We will draw that and see if mathematically it adds up. Actually, you know what? I'm gonna even try to draw this. I am not good at drawing things to scale here, but let's go for it. So our very first one was about 10 long, 4, 6, so something, no, I'm not going to draw. We've drawn it to scale on the screen. I'm going to screw up if I try to do this, and I don't want to lead you all astray. Okay, let's break up vector F1. Okay, so vector F1, you know what? I'll try this. So there's vector F1, and it had a value of 10 meters. Okay? We want to break it up into its x and y component. I'm going to see if my blue and purple show up here. Okay, so there's our F1x. And here's our, it's hard to tell the purple apart, but F1y. The reason I don't want to use my green and red is because those are going to be important in a little bit. So I'm going to try to use the blue and the purple here. They gave us one other little bit of information. They actually gave us the magnitude, so they also gave us the direction by giving us an actual angle here. So they gave us this angle as being 22.5 degrees. So we have some helpful information here. Now, remember that I said that opposite, adjacent, hypotenuse. So we can figure out what F1x and F1y are, okay? So the sine of the angle is opposite over hypotenuse, or F1y over F1. The cosine of the angle is adjacent over hypotenuse, or F1x over F1. We want to know what F1y and F1x are, right? We want to rearrange these. So F1y equals F1 times the sine of the angle, and F1x equals F1 times the cosine of the angle. We have the angle, we have the value, we can plug this in. F1y equals 10 times the sine of 22.5 degrees, and F1x equals 10 times the cosine of 22.5 degrees. So we can figure out what F1x and F1y are. Let's bring over our calculator. All right, make sure your calculator is in degrees. Is it gonna focus on it? No. But make sure it's in degrees or else you will get very wonky answers. I'm just gonna make a little prediction. F1x looks like it should be a lot bigger than F1y. So let's just make sure that those hold true. It looks like, I don't know, maybe 2.5 times the size of this, maybe double, somewhere in that range. Looks like it should be a good number. We don't know exactly what because I didn't draw this perfect, but I drew it pretty good. All right, we've got 10 times the sine of 22.5 for F1y. And we get 3.83 meters. Remember, this is in meters. I gave you the very first example in meters just to show you that vectors don't have to just be forces. After this, we're pretty much going to use forces and moments all the time. Okay, let's see what F1x is. 10 times the cosine of 22.5. F1x equals 9.24 meters. All right, that looks like it's a bit more than double that, so it seems like these numbers make sense to us. So we've got something now. Let's take a look at F2. Let's take a look at vector F2. And I'm going to say as it relates to y axes. Okay, I'm going to show you that we can do this either way. I'm lazy, and after today, I'm going to do everything relative to the x-axis. But they gave us the information for vector 2 relative to the y-axis. So let's see what that means. So they gave us the value of F2 right here. So that is F2 equals 5 meters. I have drawn this wrong. Don't mind me, sorry. That is our y-axis. They gave us this relative to the y-axis. There is our F2 equals 5 meters. And I'm using purple to draw our y-axis. And blue to draw our x-axis. So this is F2x. And this is F2y equals. And they gave us this relative to the y-axis and told us it was 22.5 degrees. Okay, so they gave us that information. So this is our angle, meaning that's the opposite side and that is the adjacent side. So opposite over hypotenuse is sine. So the sine of our angle equals F2x over F1. And the cos of our angle, which is the adjacent side, equals F2y over F1. Up here, look at this. Our y-axis was sine and our x-axis was cos. Here, our x-axis is sine and our y-axis is cos. I find that a pain in the butt. I would prefer to always have it be a simple, continuous way to do it. So I'm going to redo this one in a minute after we find the answer relative to the x-axis, just because I'm lazy and I want to not have to think. I want to think once the very first time I do this and never have to think again. So let's take a look what happens when we rearrange these. All right, so F2x equals F1 times the sine of our angle, or 5 times sine 22.5. So 5 times the sine of 22.5 is 1.91 meters. And F2y equals, let's rearrange this, F1 times the cos of our angle, or 5 cos 22.5 degrees. 5 times the cos of 22.5 degrees is 4.62 meters. Let's take a look at this. It looks like F2y should be bigger than F2x. Let's write these values in. We have 1.91 meters and 4.62 meters. So that looks like these numbers match roughly what we had estimated. Let's try doing it relative to the x-axis. Let's do vector F2 as it relates to x-axis. Again, I'm just repeating this, but I'm going to do it a slightly different way that I'm going to suggest you always do. It's just me being lazy, but it takes no more work, and it means that you're going to have a pretty good system that you can fall back on all the time. Okay, let's draw the exact same thing again. So here's F2 equals 5 meters. I'm going to draw F2x. And I'm going to draw F2y. It's still the same two vectors. That's the same, and that's the same. I've just drawn their tail to tip order slightly different. But here, I need to know what that angle is. Well, they gave me this angle. 22.5 equals gamma. This is a right angle triangle. A right angle triangle is 90 degrees. If we want to write this relative to the x-axis, which I do, because I want to be lazy and always have sine be for the y-axis and cosine always be for the x-axis, I am going to figure out what this angle is to relate it to the x-axis. Well, if that's 90 degrees, gamma prime is 90 minus 22.5. Minus 22.5, we're left with 67.5 degrees. So now I can just talk about this relative to the x-axis. I'm going to use my new angle, but it is directly related to the fact that this was given to us from the y-axis. So now we know that the cosine of gamma prime is, well, I'm going to start with sine just because I'm lazy here. Okay, sine gamma prime is f2y relative to f1. So we've got opposite over hypotenuse. Cosine of gamma prime is f2x relative to f1, or sorry, f2. These should both, all of these should be f2. What a pain in the butt I am. Those are all f2. So we now have our adjacent side relative to our hypotenuse. So we can use our cosine. So now let's calculate these out. f2y equals f2 times the sine of our gamma prime, or 5 meters times the sine of 67.5 degrees. And f2x equals f2 times the cosine of our gamma prime, 5 times the cosine of 67.5 degrees. Okay, we can calculate these out. 5 times the cosine of 67.5 is 1.91, and 5 times the cosine of 67.5, sorry. I am jumping the gun on which calculation I'm doing. 5 times the sine of 67.5 is 4.62 meters, and 5 times the cosine of 67.5 is 1.91 meters. Okay, let's see what that gave us right here. So f2y, 4.62 meters. f2x, 1.91 meters. f2x, 1.91. f2x, 1.91. f2y, 4.62. f2y, 4.62. So it doesn't matter if we do it relative to the y-axis with an angle or relative to the x-axis with an angle. You will get the same answers. I am lazy and I am always going to do it relative to the x-axis. So if the angle I have is relative to the y-axis, I'll turn it into an angle relative to the x-axis. All right, we still had one more vector that we needed to take a look at. vector F3. So vector F3, ooh, this is interesting. Vector F3, its value is 7.5. It's going in a backwards direction on us here. It'll be interesting to see what that means. They gave it to us relative to the x-axis as 45 degrees, and F3 had a value of 7.5 meters. We want to break this up into our y component, F2y, and our x component, F3x. Why do I keep writing the wrong number? So that's supposed to be F3. F3y and F3x. So we want to break F3 up into F3y and F3x. Anybody remember anything about right angle triangles when they're at 45 degrees? Any estimates on the values of these and how they relate to each other? I can hear Dave in a meeting upstairs. He didn't shut the door. So we're going to have answers that look like they're going to be about the same. Some of you who remember 45-degree angles might remember that they'll be exactly the same. Okay, let's take a look at what we get when we do it mathematically, though, because I just want to show you that if we can get good at this mathematically on some of the easier ones, we're going to start to be able to do it really quickly. Okay, opposite relative to the hypotenuse is sine. So sine of, which angle were we drawing here? Equals F3y divided by F3. And the cosine of our angle is adjacent and hypotenuse. So F3x divided by F3. So we can rearrange these so that F3y equals F3 times the sine of our angle, or 7.5 times the sine of 45 degrees. And F3x equals F3 times the cosine of our angle, or 7.5 times the cosine of 45 degrees. Let's plug that in. 7.5 times the sine of 45 equals 5.30 meters. And 7.5 times the cosine of 45 degrees equals 5.30 meters. So it looks like both of these values are exactly the same, which matches out what we've drawn. So that works out well. Okay, let's talk about adding these all up. All right, let's look at adding up our x values here. Okay. Add our x vectors. All right, let's add up our x vectors. So this one over here, we had 9.2x. So we had 9.2x. That was F1x, was 9.24 meters. F2x was 1.91 meters, and F3x is 5.3 meters, but look at this. So we've walked here, and now we're walking back. F3x equals 5.3 meters. If we were drawing these tail to tip, remember this would be right on top of these, it would be the same as just getting to there. okay? Mathematically, you understand that. You go this way, then you go this way a little bit more, and then you come back. What we're saying is fx equals f1x plus f2x plus f3x equals 9.24 plus 1.91, but that f3x is going in the other direction. We're 5.3 meters in the other direction. Here's where I'm going to say that we will always say everything going in that direction is positive and everything going in that direction is negative. It's going to make our life a little bit easier. Let's add this up. We've got 9.24 plus 1.91 plus 5.3. Whoops, that's a minus 5.3 equals 5.85 meters. Okay, now let's add up our y direction vectors. So let's take a look at our images here. Let's add y vectors. So if we're adding up our y vectors, we know we had our very first one, which was not that big. So f1y was 3.83 meters. f2y, which was down here, f2y equals 4.62 meters, and f3y equals 5.3 meters. So if we start here and walk all the way to here, our final point is right there. We can add up our y vectors. So f1y plus f2y plus f3y is going to equal fy. We've got 3.83 plus 4.62 plus 5.3 equals, so 3.83 plus 4.62 plus 5.3 equals 13.75 meters. We now have our we can now figure out our total vector. So we have a vector in the x direction that is 5.85. 2, 4, so almost 6 meters. So this is fx equals 5.85 meters. And we have our fy, 2, 4, 6, 8, 10, 12, almost 14. Fy equals 13.75 meters. We know that f, our total f, must be something along that lines. We can figure this out. We need to know its value or its magnitude and its direction. So we need to know those two things. We want to know its value and we want to know its direction. All right, well, its value, this is the opposite side, this is adjacent side, this is a 90-degree angle. We can figure out what f is. F equals the square root of fx squared plus fy squared, or the square root of 5.85 squared plus 13.75 squared. Let's calculate that. So the square root of 5.85 squared plus 13.75, squared equals 14.94 meters. And its angle, we have opposite over adjacent, which is tangent. So tangent of the angle equals opposite over adjacent. We want to know what the angle is. So we need the inverse tangent. So our angle equals 10 minus 1. F1 is 13, or Fy is 13.75. Our adjacent side is Fx, or 5.85. We can figure out our angle. So our second function, and we get 66.95 degrees. That looks about right. That's 90, that's 45. That seems somewhere in between there. Let's take a look at, so here it is all worked out for you again. Let's take a look. Well, look, that's the arrow we had drawn by doing it from tail to tip method. And that seems to match the values that we calculated. So this looks pretty good. Our graphical estimation of it seems to match pretty well with our calculated actual values are. So it looks like we did a really good job here. Okay. So equilibrium is another way of saying that this thing is static. So we've summed up what all of our vectors are on something. But if we don't want something to move, so if I am a vector of force pushing down into the floor, there is something stopping me. We know it's a joist, but it's the same thing as if we assume that I'm a vector pushing down a force, there must be something pushing up or stopping me from going down. And we call that a reaction. A reaction is still a vector. It's a type of force, in fact, but it's just the type of force that we give a particular name reaction because it is the thing that is supporting us. So if what we really want to do is prove that things aren't moving, maybe the thing we want to do is to figure out what value do we need to stop us from moving. What reaction do we need? How much force does that joist need to be able to push back up with to stop me from going down into the joist? What value does it need right there to be able to support? So equilibrium. Each structure is subjected to a series of loads that try and move the structure, whether it's self-weight, live loads, winds, snow, earthquake. We want the structure to not move or remain in equilibrium. To remain in equilibrium, there must be an equal and opposite force to keep it in place. This is called a reaction. So if I'm pushing down and the joist is pushing up, what's the total value of all of those forces in the y direction? It's got to be 0. If it's not 0, it's moving. If there is wind force pushing this way and there is a building that we need to not tip over, what is the sum of those to not move? It's got to be 0. So what we're really saying is that the sum of all of the forces up and down have to be 0, and the sum of all of the forces side to side have to be 0. If we're applying loads and we can't have it move, there must be a reaction that is stopping it from moving, and it must have an equal and opposite value. So if this is our force pushing on this object, we need something with an equal and opposite value to stop it from moving. So we want the sum of all of the forces to be 0, and we're talking about along this imaginary axis. So the force 1 is pushing in this direction. The total has to be 0. So force 1 plus some unknown reaction has to equal 0, or else this is going to move. We don't want it to move, so we need to figure out what that reaction is. So F1 equals the negative of R1. So let's just take that and draw it in the opposite direction. Fantastic. We have figured out what reaction we need here to stop this thing from moving. What if we broke this out into principal axes? What if we looked at the x component of this pushing in this direction and the y component pushing in this direction? Well, we would have needed an x component reaction pushing that way and a y component reaction pushing that way. So we could do this by breaking it up into x and y's even still if we needed to. Okay, sum F1 and F2 and solve for the reaction. I'm trying to remember if I should do this one looking down or if this one's just quick enough to do pretty easy. Yeah, this one, I don't do any values with it. So I'm not going to turn my screen down. I'll do that when we get into the ones with numbers. Okay, we've got F1 pushing down and F2 pushing this way. So F1's pushing down in the y-axis and F2 is pushing that way in the x-axis. Remember I said, look, actually that's actually really, okay, so look at this. We've got our axes drawn. See the little arrow here? We're saying that everything in this direction is positive and everything in this direction is positive, meaning F1 is pushing down or negative and F2 is pushing in this direction or negative. Let's just draw it. Let's do it with our vectors here. We've got F1 and F2. We know that our total force F, we can draw our tail to tip method, and this is our value. We need an equal and opposite force to stop this thing from moving. So this is our total force acting on it. The equal and opposite force needs to be going in the opposite direction, or F plus R has to be 0. 0 means not moving. That thing is not moving. So F1 plus 2 equals negative R. Yeah, we can do that. Well, we could have done it by figuring out what our reaction in X was and our reaction in Y was, and then solving for R. So you can do it two different ways. You're going to get the same value. So let's try it that way. Here's our F1 downwards and our F2 in the x-axis. F1 plus R1 has to be 0. So F1, R1, we're going to get negative R1. F2, we don't want it to move in this direction either. So this was saying we don't want it to move up or down. This is saying we don't want it to move back and forth. So F2 plus R2, some unknown reaction, has to equal 0. So F2 is going to have an R2 reaction. So this is our force down, this is our force sideways. We need two reactions. We could sum those up if we wanted. The square root of the sum of the squares of both of those, great. We need this reaction to stop this force from pushing down and this force from pushing that way. So we can figure out the total and then the reaction, or we can figure out the individual reactions and then figure out the total reaction. Let's take a look at this one. Does this one have numbers? No, this one's a visual. Okay, F1, F2, and F3, all pushing on this object. Let's sum these up. Let's draw our tip to tail. We've got F2, we've got F1, and we've got F3. So we started our tail, ended our tip. There is our total. We need an equal and opposite force to be our reaction. So there's our equal and opposite force. So this is what it takes to stop these three forces from making this object move. So we need this ability right here to stop these three forces from making our object move. So our object that we looked at before, or those three forces we had acting at this point right here, the sum of all of our forces was 14.94 meters, and we knew its direction. Well, our equal and opposite reaction is going to be 14.94 because it's equal and in the opposite direction. So this is what we need to stop this object from flying off in that direction. So if that's trying to lift up, we're going to hold it down with something to stop whatever that imaginary object is right there from moving. Okay, let's do some mathematical examples here. Okay. Make this bigger. Well, actually, let's start by talking about it. We've got F1 of 2 kilonewtons pushing on our object in this direction. So we know there should be an equal and opposite reaction here. And they've given us a value. And F2 of 5 kilonewtons pushing in this direction. So we need a reaction here. And then we could add up those two reactions. Or we can break each of these into their x and y components, sum up our x's, sum up our y's, and then find the reaction needed for those, and then find the total. Look at this direction. It's given it to us all the way from over here. We wouldn't really have a 90-degree angle there, so we might want to think about this relative to this side of the x-axis. But let's go through that process here. So we'll make my sheet of paper bigger, and we'll start the math process here. All right. Let's start by redrawing our problem. We've got a blob of some sort right here, and it is acting with, actually, you know what, I'm going to draw it in green. I'm going to try to draw my forces in green. So this is F1, it is 2 kilonewtons, and this is F2, and it is 5 kilonewtons. We've got an axis here, that's the y-axis, and that's the x-axis, and that direction is positive and that direction is positive. They also gave us some angles here. So they told us that this is, let's see if we can maybe make that a little bit flatter for you. That is 70 degrees, and they gave us this big angle as 120 degrees. Okay, let's take a look at F1, and let's break F1 into its x and y components. So there's F1. We want to break it into, I think I used blue for x last time, so I'll keep doing that. There is our F1x. And there is our F1y. And we have this angle here as 70 degrees. Well, we've gotten pretty good at this. We know that F1y equals the sine of our angle times F1. We know that F1x equals F1 times the cosine of the angle. I don't know why I wrote it that way. That was annoying. So we know that if we're keeping our angle relative to the x-axis, our y portion is going to use the sine and our x portion is going to use the cosine. So we're getting a little bit better at this. F1 had a value of 2 kilonewtons times the sine of 70 degrees, 2 times the cosine of 70 degrees. We have our x and y components. 2 times the sine of 70 degrees, and we have 1.879 kilonewtons. But wait a second, let's just, for our own kind of mental process here, F1y is pointing in what direction? F1y is pointing downwards. We have said everything pointing downwards is negative. All right, that's going to be handy to kind of keep track of later. So then let's figure out our 2 times cos 70 is 0.684 kilonewtons, and it is acting in that direction. Again, we've said everything acting in that direction is negative, because look, upwards is positive and to the right is positive. So anything to the left is negative and anything downwards is negative, just to kind of help keep track of things. F2, we can break this up into F2x. I did break these. I did use the wrong color, so pain in the butt. F2y. And they gave us an angle that came all the way over to here. I want to know what this angle is. A full flat line is 180 degrees minus 120. So we have 60 degrees left right here. So this is 60 degrees relative to our x-axis in a way that allows us to look at a right angle triangle. Once it's to the x-axis, we can use sine for our y component and cosine for our x component. So F2y equals F2 times the sine of our angle, and F2x equals F2 times the cosine of our angle, or 5 kilonewtons times the sine of 60, 5 kilonewtons times the cosine of 60. All right, 5 times the sine of 60 equals 4.33 kilonewtons. Let's talk about what direction that goes. F2y goes down, which we know is going to mean negative. F2x is 5 times the cosine of 60 is 2.5 kilonewtons. It goes in that direction, which is actually positive. Okay, I am going to write some terminology here that's going to throw you off for whatever reason, but just stop and think about it. We want to know what it takes for this thing not to move this way and not to move this. So not to move up or down and not move back and forth. So we want to make sure that the sum of all the forces, so that means sum, forces equals 0, and we're going to talk first about the x-axis, so everything going in this direction, back and forth, so fx, and everything going in that direction is positive. We also want to make sure that the sum, so sum of all of the forces in the y direction equals 0, and everything going in the upwards direction is positive. So this is just saying we don't want it to move back and forth, And this is just saying we don't want it to move up and down. All right? We want to know what it takes for this object not to move because these forces have been applied to it. This is just a fancy way of saying that there must be something stopping it here and we don't know what that is. Okay. Let's look at the things we know are acting on this in the x direction. Well, in the x direction, we have F1x. So we have F1x, and we have, I'm trying to see what way I did this in I don't really like the way I've written this out. Yeah, I don't like the way I have it written in there. So we have F1x right here. So F1x is acting in that direction, which we know is negative. So we're going to have minus F1x, and we have F2x, which goes in the positive direction, or plus F2x. But we know there must be something stopping this from moving. We don't know what it is, but there's some x component. So plus some rx. We don't know what it is. We don't know what rx is. We're going to guess that it's going in the positive direction, but I really have no idea. Well, we know what F1x is. F1x is minus 0.684, and F2x is 2.5, and Rx, we still don't know what it is. Well, Rx, if we rearrange all of this, we have minus 2.x plus 0.684. We have minus 1.816 kilonewtons. So we must have something pushing in this direction with a value of 1.816 to stop this object from moving. Let's take a look at our y-axis. All right, we want this thing not to move up or down. We've got our F1y pushing down, or minus 1.879. And we've got F2y pushing down, or minus 4.33 kilonewtons. We need something pushing upwards, we think, or some unknown thing in the y direction to stop this thing from moving. And 0 means that it has to be not moving. We don't know what would stop this from moving, but we need our y. Our y is 1.879 plus 0.3, or 6.179 kilonewtons. So we need these two reactions to stop this thing from moving. Now, you could figure out what the sum of F1, the sum of the x's are, the sum of the y's are, figure out what the total force acting on it is, and then figure out the equal and opposite reaction. You can do this in different orders. The example that's in the slideshow, I did in a different order than I'm doing right now. And the only reason is that I want to show you that it doesn't matter what order you do it in, you're going to get the right final answer. And sometimes, depending on what we want to do, one order might be better than the other order. So now we want to figure out what the total reaction is. We figured out what the x component of the reaction is. We know we need 1.816 kilonewtons pushing in that direction. And then we need 6.179 kilonewtons pushing upwards. So let's draw what that looks like. Okay, so we've got our object here, and we know that we need kilonewtons pushing in that direction. And we need 6.179 kilonewtons pushing in that direction to give us our total reaction to stop this object from moving. And it would be handy to know what direction that is acting in. Well, look at this. We've got a right angle triangle. We've got an angle here, opposite, adjacent. Well, we know when our angle is relative to our x-axis, things start to get really easy. All right, we have, we want to find out the total value, right angle triangle, where opposite and adjacent have values. We can just use square root of the sum of the squares, or 6.179 squared plus 1.816 squared. We can plug this into our calculator. Square root of 6.179 squared plus 1.816 squared equals 6.44 kilonewtons. And so that's our magnitude. And our direction, let's call this angle gamma. Well, the tangent of gamma is going to be opposite over adjacent, or 6.179 divided by 1.816. So our angle is the inverse tangent of 6.179 divided by 1.816, and we get 73.6 degrees. So we know this is the reaction that it takes to resist these two loads. So this object has these two loads acting on it, and we need this reaction to resist it. Okay, these were the components of it, but we need this total reaction to resist this load. Now, here it is worked out in the slideshow. I did it in a different order within this, just to show you that you can do it by figuring out what the total force is and then determining the reaction. And in fact, it looks like I did it both ways, even in this. Okay, here it is drawn out graphically, more or less to scale. All right, let's just talk for a second, going back to that mass times acceleration. All right, let's bring this back up to me. Okay, so the way we think about different reactions, or the way we resist different loads, kind of helps us kind of figure out a few things. So I'm just going to talk through how objects resist different loads. Now, weight, or the load of us pushing downwards, has a reaction. Remember, force is mass times acceleration. Is a body at rest experiencing no forces since it's not accelerating? I'm not accelerating anywhere, but I'm sitting here. I'm not going anywhere. A body experiencing no force is still trying to accelerate to the center of the Earth at a rate of 9.806 meters per second squared. This is the acceleration due to gravity. Right now, my body is trying to accelerate into the center of the Earth. All of you are, right now, trying to accelerate into the center of the Earth. That means I'm being held in place by a force equal to my mass times the acceleration due to gravity. This is the reaction to weight. So my weight, W, is mass times gravity, and there must be a reaction to that weight, or that force. Okay, let's just take a look at what that means. This is more just to show you or illustrate a point. I really want your head to get around reactions. This is a really important thing for engineers to understand in material science and physics. Not so much for you guys. I just want this to be a quick exercise to kind of show you where this all comes from. So here I am standing on Earth, I have a weight, I have a mass, which would be in kilograms. I'm trying to accelerate into the center of the Earth. I can figure out what my mass times the acceleration caused by Earth acting on me has to figure out what force I'm pushing down on the Earth with. And then I need some reaction to stop me from accelerating into the center of the Earth. For me right now, my chair needs to be able to resist that force. Okay, so let's say I weigh 140 pounds, or I did a year ago, not so much right now. So I have a mass of 140 pounds. We can turn that into kilograms. So that's 63.5 kilograms. My weight is my mass times g on Earth, or the acceleration on Earth, or the amount I'm trying to accelerate into the center of the Earth, or 9.806 meters per second squared. So we can figure out that my weight is 623 newtons, which it's a pain in the butt to kind of often talk about newtons. We like to talk about them in kilonewtons. So 0.623 kilonewtons. That is the force I cause pushing downwards, just sitting here, not doing anything at all. That means my chair has to be able to resist, or it has to be the reaction for me pushing down. So if this is the seat of my chair, I'm pushing down on it. There must be something pushing up. In fact, there's two sides to my chair. Maybe that's something we can use next week to talk about what if the reaction isn't directly under me? What if there are two spots supporting that load? Well, what if I flew to the moon? All right, me and Elon Musk were pals, and I get in one of his spaceships and I head off to the moon. Well, on the moon, the acceleration due to gravity is 1.6 meters per second squared. So on the moon, I would push down with a different force. I have the same mass, and mass is all about displacement of body of water. My mass times the acceleration, or we can figure out what that is in kilograms. So we can take my mass and turn it into kilograms. That doesn't change. My weight, though, on the moon, I'm accelerating into the center of the moon at a different rate than I'd accelerate into the center of the Earth. So on the moon, I only cause a downward force of 0.103 kilonewtons. That means a chair on the moon would have to resist less load caused by me than the same chair on Earth. Now, that's a slightly ridiculous design scenario, but I just wanted to illustrate something there. Okay, those both worked out. Now, wind and reaction. Wind is basically air in motion. It's a fluid medium with a mass. It has a ridiculously low mass, but it has a mass nonetheless. Wind causes a force when it interacts with a body or a structure because the wind must produce an acceleration on the air particles to move around them. So this concept of what's accelerating is slightly different when we're talking about wind. So basically for wind forces, the body doesn't accelerate. The body makes the wind mass accelerate. So we become the chair in a way. We're not going to worry about it too much. We still have to be able to resist that same force. Earthquakes and reaction. In earthquakes, the body is accelerating. The earth moves, making the body move with it. The earth is exerting a force on the body, causing it to move. So the earth's moving and the body is going along for the ride. To make it easier, we consider our reference point to move with the earth. This lets us consider the body anchored to the earth to be static, while our frame of reference accelerates due to the earthquake, similar to gravity, which is why we take a percentage of our downward force as a relation to it. So we think about it as a percentage of gravity acceleration causing a lateral acceleration. We draw it as if we have kind of a static situation happening, even though it's not. This is why we consider the earthquake forces to be some relationship to the mass of the building. This relationship is the acceleration produced by the earthquake. Okay, so we have the acceleration due to the earthquake that we multiply by our mass to get the force the earthquake causes on the object. Pressure and reaction. When air or a fluid is held in a vessel, it's not in its natural state. That gas wants to get out. It's trying to push out. The more you compress it, the more it tries to push out. For water in a glass, the particles are trying to accelerate out and also downward because gravity is exerting a force on it. So that's why it's trying to push out at the bottom more than it's trying to push out at the top. Similar to our soil trying to get into the void in our basement. To resist the particles accelerating out of the vessel must exert a force on the fluid or the air mass to maintain equilibrium. Now, we're not really going to do anything with these, but I just wanted you to think about that as an exercise. It sounds like someone's knocking on my door, but I don't see anyone there. All right, let's do a quick example. All right. We're going to do two quick examples here. And this is really the end of it for today. And these are not hard examples. Actually, I know what it is. The inflow valve for our toilet upstairs is leaking, and it's been slowly getting worse. And it sounds like it's happening a lot worse right now. Okay, so you're standing in your living room when an earthquake hits. The quake produces a lateral acceleration equal to 15% of gravity. So it's trying to accelerate the earth that way, about 15% of what it's trying to push it downwards. It's just after the holidays, so you're carrying a bit of extra weight, topping the scales at 85 kilograms. What is the reaction required for you to maintain equilibrium, magnitude, and direction in kilonewtons? So let's take a look at this. All right, we have an object that has some force acting on it. So this object has a downward component due to its weight and some lateral component due to earthquake. So it's trying to be pushed that way by some amount to the earthquake, but also there's the normal old gravity loads pushing downwards. So W is m times acceleration due to gravity. They gave us the mass of 85 kilograms. And we know gravity due to, or the acceleration due to gravity is 9.806 meters per second squared, or 85 times 9.806, or 833.5 newtons. We often like to write these things in kilonewtons, so 0.833 kilonewtons. The earthquake component to this is our same mass, but we're being moved by only 15% of the acceleration due to Earth, or 85 kilograms times 0.15 times 9.806. What we often do, because we're lazy, is multiply this out first and then just multiply it by the 15%. But what we're really saying is that it's 15% of the acceleration due to gravity. So here we have 85 times 0.15 times 9.806. Oh, sorry, I forgot the multiplication. 85 times 0.15 times 9.806, or 125 newtons, or 0.125 kilonewtons. We want to know what the reaction is to resist this. Now, I'm going to draw it this way. So we want to know what the total force acting here is. So let's figure out what the total force is. Total force is the square root of 0.833 squared plus 0.125 squared. Square root of 0.833 squared plus 0.125 squared is 0.842 kilonewtons. So really what we're saying is we have some applied force that's moving this amount some and this amount some. So we've got an applied load that's acting like this. So this is our total force, and it would be handy to know what this is relative to the x-axis here. Okay, we can figure out what that is by always being lazy, and the tangent of our angle is going to be our y component divided by our x component, or our fy divided by our fx. So our angle is tan minus 1 divided by 0.833 divided by 0.125, or our tangent, our second function tangent, 0.833 divided by 0.125 gives us 81.47 degrees. So we know what that force is. I'm going to be lazy here. If this is our object, we need an equal and opposite reaction, where that is 81.47 degrees, and this value is 0.842 kilonewtons. So that's our reaction. We have a force acting on this object, which is us, and we have a reaction acting on this, which is us. Now, if this is a person, where does this actually get applied? Somewhere about here on their body, eh? Our center of gravity, our center of our body, or our center of mass, if you want to think of it that way. So it looks like there's some stuff we still don't understand. This is something we should probably talk about next week. How do we deal with this situation? And we'll come back to this next week. Okay, we have another problem we're going to solve that is going to be a part 1 that we'll talk about next week. All right, a billboard is 5 meters high and 10 meters wide. It weighs 0.5 kPa and experiences a wind load of 1.2 kPa. Calculate the reaction required to maintain equilibrium for the billboard. Okay, so this was earthquake, and here's wind. All right, I know this was something that people struggled with last week. How could you have an area acting downwards over a surface? Well, here's our billboard, okay? And we're saying it's right on the ground, and it is 5 meters high, and 10 meters wide. And we are saying that every meter by meter squared weighs 0.5 kPa. So this little tiny blob weighs 0.5 kilonewtons. Each one of these little tiny blobs weighs 0.5 kilonewtons, and they're all acting downwards. We can say this total billboard has a downward weight of 0.5 kPa times 10 meters times 5 meters, or our area. 0.5 times 10 times 5 is 25 kilonewtons. So this board weighs 25 kilonewtons, okay? They've also told us that there is a wind load pushing on the billboard with some force. And they told us that the load acting on it is 1.2 kPa. So 1.2 kPa. So every 1 meter by 1 meter square of this billboard has 1.2 kilonewtons of load trying to push this billboard over, or 10 times 5. So 1.2 times 10 times 5 equals 60 kilonewtons. So this billboard is trying to accelerate down into the center of the earth, and that results in a force of 25 kilonewtons downward. Meanwhile, it's a windstorm, and the wind is trying to push this billboard over with a force of 60 kilonewtons. All right, so we have some object here, and we have a load acting on it and a weight pushing down on it. So we have this trying to be pushed over, but also trying to be pushed down. So we have a load acting on this billboard. This is 25 kilonewtons, and this is 60 kilonewtons. All right, we want to know what the total force is. It's going to be the square root of 25 squared plus 60 squared. Or a total of 65 kilonewtons. And we want to know what this angle is relative to the x-axis. We know it's the tangent minus 1 of the y component divided by the x component. Or the inverse tangent of 25 divided by 60, or 22.6 degrees. That means we need an equal and opposite reaction pushing back that has 65 kilonewtons, and it is also 22.6 degrees off of the x-axis. So an equal and opposite reaction to resist that load. Again, there seems to be something funny here. This billboard, that weight is somewhere up here. So there seems like there's something more we can do with these two problems next week. Okay. So what are our takeaways? Statics. The system is in equilibrium. It is not moving. It is not moving up and down. It is not moving side to side, and it is not moving in and out of the page. We have an object that is not moving. That is what we want for our buildings. If it's moving, it's not in static equilibrium, and we've got a problem. So remember, for your project, when you pick your object, you want to make sure it is in static equilibrium in all the directions. You're going to draw images that illustrate that. You don't have to do math for it though. I'm not making you do math for that part. Remember that vectors have magnitude and direction, or a value. We're often talking about force, so usually something in kilonewtons, but it could be moment. Force is a vector. Forces can be rewritten into x and y components. And to not move, there needs to be an equal and opposite reaction. So a lot of those are similar to our studying tips. You should know how to break those vectors down into x and y components. You should know how to determine the magnitude and direction of a force or multiple forces. And you need to remember that everything needs an equal and opposite reaction to be in static equilibrium. Next week, we're going to talk about this idea of things wanting to tip. And we're going to talk about how we can deal with static equilibrium when something wants to tip over. So there must be something else going on there. Basically, so far, we've talked about 3 degrees of freedom. We've talked about moving up and down, side to side, and in and out of the page. Now we're going to talk about spinning in all of those directions. So spinning like this, and spinning like this. We're going to start talking about 6 degrees of separation. Okay, so next week we actually do some really fun calculations, which I'm really excited to do with you guys. So we'll start those next week.